So welcome everyone to this edition of Verifiability Talk. It's my honor to introduce today's speaker, Kerstin Eder. Kerstin is a professor at University of Bristol. She leads the Trustworthy Systems Laboratory there, and she has a long-standing experience with design automation, all sorts of verification techniques, including formal verification, but also simulation-based verification applied to functional and non or extra functional properties of systems, including energy aspects. And she will be talking about intelligent testing, particularly applied to robotic and autonomous systems and AI-enabled systems. Kerstin, thank you very much for having accepted our invitation, and the floor is yours. Before I just give the floor to you, please note that this talk is being recorded and it will be posted on YouTube. For example, your initial or your name might appear in the recording. If you're unhappy with that, please note that that might appear in the YouTube recording. Thank you.
Thank you very much. Thanks for the invitation and for your kind introduction. Hello and welcome everyone to this seminar. I'm very excited about this opportunity. I've got two main objectives today. For those of you who are involved in task verifiability, I aim to give you some insights into test automation and in particular how to use AI in order to make test generation smarter. And for those who've just attended out of interest, hopefully you will learn, or I promise you will learn how testing can be automated so that next time you are tasked with testing, you do a much better job than before. So let's get started. I lead the Verification and Validation for Safety in Robots research team at the Bristol Robotics Lab, but as you've heard in the introduction, I also lead the Trustworthy Systems Laboratory here in Bristol. Now, in the Trustworthy Systems Lab, we take the view that trust can be gained and lost, and regained and lost again, as we all know, but trustworthiness should always be demonstrable. So there are different ways of convincing yourself that a system is trustworthy, and in our research group, we are exploring and researching techniques that help designers and verification engineers obtain the evidence that is necessary for others to be able to trust systems. So confidence in a system's trustworthiness can be gained in a variety of different ways. One of those is by design. So systems that are simple can typically be understood, and therefore simplicity and clarity of both the design as well as the implementation are some of the research core research areas in the Trustworthy Systems Lab. And I consider this by design topic a really important and key aspect for verifiability. But in addition to this, confidence in a system's trustworthiness can also be gained through transparency. So if we can get an insight into how a system makes decisions, how it uses resources such as time, energy, or power, or why it acts in a certain way, that can make a system understandable. And so part of the work in the Trustworthy Systems Lab is focused on transparency of energy consumption in a system. So what we see at the bottom here are 4 heat maps. And from the left, starting from the left, we have the AND operation, subtraction, shift left, and logic AND. Okay, so these are machine instructions, and these are heat maps that show us how the machine dissipates power or consumes energy, if you want, when executing these instructions. And while the rightmost one, the logic AND over here, might be the most pretty, and it won us an art competition, I'd like to focus our attention in terms of transparency on the one that is half blue and half red, which is subtract. Okay, so if we focus on this, then what we see here is a subtract operation where on the y-axis we've got operand 1, and from that operand 1 we take off the operands on the x-axis, which is operand 2. Okay, so if we just pick one, namely 160 for instance, then you can clearly see that as long as we are taking values of that are smaller than 160, which is shown here with this yellow arrow, then we remain cool, so that consumes little energy. However, as soon as we go to values that are 160 and over, we suddenly are high in energy consumption. And normally, if this was a live session, I would ask you why this might be. So those of us who understand how two's complement works might see that as soon as you flip and you get to negative results, lots of bits will flip, and that consumes a lot of energy. And it's this transparency that we need to understand, because we might be able to shift our computation into the blue space if only we knew this would happen. Okay, so this transparency allows us also, in the grand scheme of things, to, for instance, compare 32-bit data on ALU instructions with 8-bit data. And you can see that 8-bit data creates a much lower energy footprint for all types of ALU instructions compared to 32-bit data, which you see on the left. So next time you write int x, think about whether your loop actually only goes to 10 or 100, and whether you really need 32-bit data, or whether something smaller is sufficient to save the planet. And it's this transparency that we are investigating. But today we want to look at something completely different. Today we really want to look at verification and validation, which are, of course, core aspects of gaining confidence in a system's trustworthiness. Now, to start with, let's clarify some terminology. It is my experience that when one talks about verification, especially in the software domain, what people often hear is formal verification. But according to the standards, verification and validation are classified, or techniques for verification and validation include formal methods, as well as testing, as well as different types of analysis. So when I talk about verification, I mean the process used to gain confidence in the correctness, security, safety, whatever you name it, trustworthiness of a system. And that is the common understanding in the hardware domain, where they typically do not fix a priori the type of techniques they are using in order to gain such confidence. Okay, so when I talk about verification, I include all of these techniques. So for the group, we focus on rigorous proof, and we complement this rigorous proof by simulation-based testing. And in particular, we are interested in finding advanced test generation methods and ways of achieving a high level of automation so that we can gain confidence in the correctness and trustworthiness of a system. Now, it's typical that you consider a variety of techniques, as we've just seen from the standard. And I want us to look very briefly at the variety of system models on the horizontal axis. You have formal models, physical models, and in between you've got simulation. And on the green vertical axis here, we've got different types of ways of expressing requirements, from textual requirements via assertions down to logical properties which are formalized. And these are effectively interacting with each other, or are being used in formal verification, simulation-based testing, and then also in real-world experiments or lab-based experiments, for instance. So what I want to focus on today is simulation-based testing. Now, the challenges when it comes to robotic and autonomous systems are quite interesting, because we have complexity both in the software as well as in the hardware side. We have very high levels of concurrency. We also have temporal aspects, and unfortunately, experiments are expensive and often unsafe. And this becomes even more important when we consider the involvement of people and different actions of the environment that we simply can't control. So in this context, then, we are investigating techniques that are well established in microelectronics design verification, in particular coverage-driven verification, to verify code that controls robots, as well as autonomous vehicles. Now, if you've got questions, please ask in between. If you have a question, I'm very happy to be asked questions as we go along, but I can also answer questions at the end if you wish. So what I would like to do first is to focus on coverage-driven verification, which increases the level of automation in simulation-based testing. What we see here is a coverage-driven verification test bench for human-robot interaction in particular. So I want us to understand the entire picture, and so we're going to pick out some boxes to concentrate on to gain an understanding how this works. And I'll start with the code that controls the robot. Now, robotic code tends to be quite complex, and there are typically lots of interactions between the various modules that control the different parts of the robot. It is interesting and really good to see that increasingly finite state machines are being used in order to describe robotic code. And we've seen a presentation from Anna Cavalcanti recently that promoted this approach. And this is really nice to see because that allows easier application of formal methods. And it's also quite useful for simulation-based verification. Ideally, in our simulation environment, we want to get as close as possible to the actual code that runs on the robot. So we have to cleanly cut this out. We have to identify the interfaces and be very clinical about this to make sure that our verification results are representative for the code that actually controls the robot. Now, what I want to focus on next is the test generation process, or the test generator as such. Now, the test generator is there in order to create tests that are effective, and it needs to do this in an efficient way. And there are different strategies to achieve this. The most basic one is probably pseudorandom test generation. I say pseudorandom because it's really important to have repeatability. And that can be quite hard to achieve, especially with the different levels of software and hardware that we're dealing with and the operating system in between. So that in itself is a challenge, and we're writing a paper on repeatability and the lack of determinism in some of the simulation environments in this community. But that's not the focus of what I want to talk about today. Constraint pseudorandom test generation is another interesting approach where we're using constraints in order to make the rare case happen more often. Now, let me describe at this point the human-robot interaction scenario that we're looking at and that we focused on in our research. So we have got a joint space scenario. It mimics a manufacturing scenario where the human and the robot have to collaborate in order to jointly manufacture, in this case, a table. And we've picked out a particular action or collaboration, namely the handover of a piece of a work piece from the robot to the human, where the robot has to make a decision as to whether it's safe to let go or not. And it does this based on 3 sensors: where the human is looking, gaze, whether the human is gripping the object, so there's a pressure sensor. The human is equipped with a glove which contains a pressure sensor, and in addition, location. So you can see there is a location wristband here, and we are using that as well as one of the sensors that helps the robot make the right decision. So we've got a collaborative co-worker environment, and we really want to make sure that the rare events happen relatively often in our simulation, such as the one on the right-hand side here, where there is a bit of a misunderstanding as to who is taking which space, and that could easily lead to a collision. Now, in terms of test generation, we've looked at pseudorandom, constraint pseudorandom, and one way of making the rare event happen more often would be a model-based technique to target specific scenarios of interest for the verification. Now, just to recap for those of us who are not that familiar with model-based test generation techniques, roughly speaking, in a model-based test generation technique, or one of those, you would represent your system, including the environment, using a formal model, in this case, state machines, and you represent both the system under test as well as the environment in such a formal model. You can then traverse that formal model and extract traces, for instance, using model checking, of how the system works. And these traces can then be traversed in order to identify test templates which include actions of the environment and how the environment interacts with the system under test. Now, these test templates can then be sequenced, and you obtain action sequences at a very high level. And these sequences then need to be parameterized, and you can obtain a large family of tests, which are then executable on the actual code. So for instance, the parameter instantiation might fix particular delays or locations or speeds, etc. Now let's focus next on the checking. Okay, so that's this part up here. For checkers, we can encode requirements as assertions, and these assertions typically have the form of if-then statements. So if a precondition is satisfied, then we expect a postcondition to hold. So if the robot decides the human is not ready to take the object, then the robot does not let go of the object. And these can be implemented as automata and run in parallel to the simulation. There are different types of options. You can do this at a very high level or at a lower level, depending on the detail that your simulation can capture. So if you've got motion planning or collision avoidance, then your simulation needs to capture this sort of thing in order for you to be able to check to that much detail. Okay, we've covered almost all boxes except for the coverage collection. So let's have a look at that as well. So in terms of coverage, the traditional metrics for coverage are code coverage or structural coverage, such as a coverage of the finite state machines that are in the code. But I want to focus more on functional coverage in this context. And this functional coverage comes from the requirements and also from the assertions that we have written down based on the requirements. And generally speaking, we distinguish between functional and safety properties. And some of these are motivated by standards. So let's have a look at this scenario in terms of the requirements that are motivated initially by standards, and then also some functional ones, starting with the functional ones. So functionality, if the gaze, pressure, and location, which are the three sensors that the robot is using in order to make a decision, are sensed as correct, then the object shall be released. And if they're sensed as incorrect, then the object shall not be released. And the robot should make a decision before a time threshold. So there's a timeout in the system, and it has to make a decision before then. And the robot shall either time out, decide to release, or decide not to release. So nothing else, because there can be errors of omission and commission, so we have to cover all angles. So these are the functional requirements that we would like to have satisfied or to check. In addition, there are safety requirements, and these are motivated by the standards, as I said before. For instance, the robot shall not close the gripper when the human is too close. The robot shall start in restricted speed and force. The robot shall not collide with itself at high speeds, and obviously also not with the human. So there is also number 8. The robot shall operate within allowable maximum values to avoid dangerous unintentional collisions with humans and other safety-related objects. So you can see these safety requirements, they need concretization and they need to be investigated and refined further for the respective scenario that you might have in mind. Okay, so these are requirements that flow into our functional coverage, but we also looked at what is called situation coverage, which is a coverage model that is based on Cartesian products, or as it is in the community, often called cross-product coverage. And these are based on the gaze, pressure, and location sensor data values. And to show you what we've done there is we have got tuples which tell us gaze pressure and location. And depending on these, they can either be correct or incorrect. Where you see a 1 right at the bottom, so there are 8 combinations of these. Right at the bottom, this is when gaze pressure and location are sensed within the tolerances, and that they are sensed as correct, which should result in releasing the piece. So that would be where we would expect coverage or a timeout if the robot doesn't make a decision within the time window. And all the others are somewhat incorrect in terms of any one of the sensors, and that should result in the object not being released. Okay, so any of the grayed out coverage points are not reachable or should not be reached. If they are reached, something's gone wrong. Okay, which is a very close interaction that you can see between the assertions and the actual coverage here. Okay, so if we then look at the situation coverage results and we compare the different test generation methods, it's not surprising that if you use pseudo-randomly generated tests, most of the tests will result, if you see up here in the green rectangle, most of those tests are resulting in a situation where neither gaze pressure or location is correct, right? So the piece is not released. If you look at the model-based tests, we can then traverse a model and we get much better coverage of the situations where the workpiece should be released, or different ways of not releasing, different reasons of not releasing the piece. And then if we constrain the model-based, then we can also get, some timeouts. And then if we put this all together, of course, we get coverage everywhere. So this is just showing us that a combination of techniques will need to be used in order to get good coverage of all the different areas that we're interested in. Okay, so now we have investigated the entire environment, and the blue test bench around the blocks that we've investigated is effectively giving us an environment. Namely, as far as the robot is concerned, that is, or the control code for the robot, that is the environment it operates in. So you can see that there is a simulated human, and there is effectively a driver that interprets the test sequence, and the driver then decides when to issue a command stimulus to the robotic code. And that robotic code then sends a response, which is fed into the checkers, and also is observed with respect to coverage. But that response is also observed by the environment, which then interprets it, and the physical implications of that response from the robot is observable by the test environment, which then motivates or triggers the next interaction from the simulated human. Okay, so it's really important that our robotic code is effectively fooled into believing it works in the real environment, which is why it's so important to not cheat when we build this test environment, right? Because the physical interpretation of the response from the robot needs to be as close as possible for the robot to then be in this continuous loop of responding to what it senses and then being stimulated again through the tests that we want to run. So in summary, coverage-driven verification is a systematic goal-directed verification method. It offers a very high level of automation. The focus is really on test generation and coverage, right? Because we've automated everything else away. Now, constraining test generation requires significant engineering skill and understanding of how the system under test is supposed to work. And model-based test generation allows targeting requirements and particular coverage more effectively than constrained pseudo-random test generation. Now, we are in the process of transferring this into autonomous vehicle verification. And what you can see here is a test bench for this domain, where in yellow we have test generation. So we have a situation-based environment where we've got a specification of a particular experiment And then we translate this into scenery. So that's the initial setup that is static, that's fed into the simulation, as well as any of the actors in the environment. And that might be other road users or, traffic lights and such like. These are dynamically changing their behavior during simulation, and that is part of our test generation. We also have coverage, different types of coverage in orange here. We've got requirements coverage, we've got code coverage, and we've also got assertion coverage. And in addition to this, we also have checkers in green. So we've got a set of assertions. We're still working on a good set of assertions, but we've got some already. These are checked through logging what happens during the simulation, and then we can find out whether our tests have passed or failed. Now, in terms of assertion checking, let's have a look at this example here of an overtake and brake scenario. I'm sure those of us who are driving have experienced situations like this. The yellow vehicle is the one that we're not controlling, and the red vehicles are the ones we are controlling in the test. And so what you can see here is a visualization of the simulation, and underneath we have what the database records. And in this database, we can then post-process the simulation results, and we can, for instance, identify a near miss, and we can exactly detect at what time in the simulation this has happened, and we can then visualize this to see what actually has happened. We also can set up different test cases. So for instance, here we've got a turn within or through traffic, with and without a cyclist. So at the top, we've got the cyclist that stops. And at the bottom, as you can see there, the cyclist didn't stop, and the yellow vehicle is the one that is offending and probably hasn't seen the cyclist. So those of us who cycle are probably familiar with this scenario as well. And then we also can see this in assertion checks. So at the top here, you can see what our database can see, and at the bottom, you can see the visualization of this, and we get traces out of the post-processing of the simulation logs, where we can see that a collision has been detected, and we can see exactly what the actors that have been involved, as well as when this has happened. So coverage-driven verification provides us with a lot of automation, and that is extremely useful, but the test generation challenge remains. Now, robots tend to be what I call responders. They are machines that learn, often black box, and we need to introduce ways of confronting them with situations in a test environment that are reactive to the way they work. So we need what I'm calling agency for intelligent testing, because robots and autonomous systems, for them to be useful, they generally need to be both powerful as well as smart. And we can see that AI and learning are increasingly used to achieve that. But I'm arguing that it doesn't really matter how clever your robot is. Testing it requires more AI than you put into your robot, because ultimately the robot or the autonomous system will be an environment that hopefully is more clever than it is itself. And so let me be really provocative. The challenge is not making your robot as smart as it could be. The robot only needs to be as smart as it needs to be to do what it needs to do. However, writing tests manually or randomly is obviously not a clever way of testing the clever systems that we're currently building. What we need is more clever AI in the test environment, so that if the robot outsmarts us, we find this in the test environment and not in the real world. So what we really need is what I'm calling intelligent testing. Now, here is an observation. We're using AI and in particular agent-based languages to program robots, in this case drones. And it's interesting how this is done. It's based on belief, desire, intention agents. So you can then capture such an agent in terms of its goals to fulfill and the knowledge that it has about the world. Okay, and these are captured in desires and beliefs. These agents also have intentions. So these are the immediate plans according to the current beliefs and goals the agents have. And when they then execute the plans, that creates the new beliefs and new goals. And that's a very interesting way of programming robots and autonomous systems. And I think this is the way we should be programming test environments. So what we really wanted to find out is, in addition to the clever ways for test generation that we have, can we use agency, in particular BDI agents, in order to harness the power of this mechanism to introduce agency into a test environment? So the research questions we have been and we are still exploring is, how can we exploit BDI agents for test generation? Can we use machine learning to automate this process? And how does this compare to traditional methods for model-based test generation? So let's have a look. Belief, desire, intention agents can certainly be used to model our human-robot interaction scenario. Okay, so we can model what the robot does as a BDI agent. We can also model the entities the robot interacts with, such as the simulated human and also all the sensors. And the interactions between these agents create action sequences from which we can harvest the material that we need for test patterns. Now, these agents all interact through their beliefs. But the question is really, which beliefs would be useful for us to get meaningful sequences of test patterns? Now, what we can do is we can introduce what I'm calling verification agents. Now, verification agents are meta-agents that can influence the beliefs upon which the agents that are in the simulation can act. And that allows us to direct or bias the interactions between the agents in the simulations. Now, the problem here is this is a very small scenario, right? We've got one robot, one human, a few sensors, and the objective is a critical one, namely the safe release of an object, but it's not really a very complex one. And there are 38 beliefs in this example. And that gives us 2 to the 38 belief subsets, which is quite a large space. So the question is, which beliefs or which belief subsets should we use in order to generate a good variety of meaningful interaction sequences? Now, there are various ways of selecting these. We can do this manually. We can randomly select them, or we can use learning. And in particular, we explored reinforcement learning, where we tried to cover all the options the robot has available. So we tried to cover any of the robot's plans and thereby identify suitable belief subsets. Let's have a look. Let's have a look at how this pans out in terms of how effective these agents are for test generation and how this compares to traditional model-based approaches. Now, to be fair, we need to consider the cost of learning the belief sets. Okay, and this is actually not too bad, because in less than 3 hours, it was possible to achieve convergence. So from our perspective, that was a cost worth paying for the results that we're going to investigate in a moment. But I want to say this just up front, because good results don't come for free. So let's have a look at code coverage. What we see on the y-axis here is code coverage for different methods. We have, first of all, BDI by hand. So we selected the belief sets by hand. Now, this basically means that there is engineering time involved, and that, of course, has the fastest growing coverage. Okay, now that's not surprising, because someone has thought about this, and that's someone who's understanding what's going on. Pseudo-random is next, and that's effective, but it flattens out before the maximum can be reached. And then we've got BDI using reinforcement learning, which is the straight through line, and that's achieving the maximum, and it does this slowly but fully automatically. And when you talk to people in industry, they say, yep, that's well worth it because I can use the brain of my verification engineers for doing something else if I can achieve what they can achieve using automation. Which is why we think, although it is slower than doing it by hand, it is definitely worthwhile doing because it does it fully automatically. And pseudo-random, just as a baseline, doesn't ever recover and goes up into the higher levels that the other three methods achieve. So it's definitely a good idea to use some sort of model compared to just doing it pseudo-randomly. If we compare this with a model checking timed automata, which is the model-based technique that I previously suggested, then in blue we've got the BDl-agents, and in red we've got the model checking. And what we're looking at here in terms of the bars is average code coverage. And we can see that the BDl-agents are actually quite good and outperform the model checking on most occasions. And with the line above, we get the maximum code coverage by any test achieved given a particular seed. Because remember, the test sequences that we are obtaining, they still have to be concretized to run a particular test. So the templates themselves, they can't be run. They have holes in terms of speed, distances, and locations, etc., which still have to be instantiated. And for that, we use random generation. So we use the same sort of seed for all of the different test patterns. And then we can see that continuously the BDl-agents seem to achieve very high coverage, which we are very happy with. Now, there's something else also to observe, and we've actually done this in two scenarios. I've introduced you to the cooperative manufacturing scenario, but there was also a home care assistant scenario, which I've not introduced you to. But for this observation, I want to show you the results for both, because what we found when comparing the BDl-agent to the model checking timed automata is that in terms of the lines of code for the models, the BDl-agents are much smaller than the models used for formal verification, or the formal models that we used for model-based test generation. And in addition, the traversal time, so the exploration time of the models, is much more stable. And that's not surprising because model checking, depending on what you're asking, can have very different response times. So we are very pleased about the stability of the BDl-agents. But of course, model checking comes with a guarantee, right? And that does not come with the BDl-agents. But it is also possible to model check agent models. So that could be used as a last resort if we do not get to the test that we are really wanting. So that's a caveat, but also an outlook, a hopeful outlook for this. So if you go back to our research questions, then we have found that traces of interactions between BDl-agents do provide test templates that can be used for test generation, and they perform reasonably well, actually surprisingly well. We have found that it is possible to use machine learning to automate the process of belief set selection, and that helps us to steer the test generation in order to achieve certain coverage and to maximize the coverage. And then finally, compared to traditional model-based test generation that relies on model checking timed automata, the BDI models are smaller in terms of their size. They are more predictable when it comes to the exploration time. They're equal, if not better, in terms of the achieved coverage, and they are far more intuitive to write because they express agency in a natural way. And from my own experience, it is a lot more fun to write these agents than to write these state machines that are used for model checking. So yeah, and in particular, I think it's interesting to see that if people use BDI to program their robots, then they can use the same language for programming their test environment. So that wouldn't then mean you have to learn a new language, such as the input languages for the model checkers, in order to do your testing. And I think that's a big advantage for uptake. Okay, so what we have proposed, therefore, is to add to the known taxonomy of model-based testing, where we distinguish the model specification types, the test generation types, and the test execution types, we have proposed to add a new paradigm, which is agency-based, to the traditional paradigms, and to also add agency as a technology for test generation alongside, for instance, model checking or constraint solving. And we have, of course, recently transferred this into the autonomous vehicle domain. Now, in this context, we have been trying to generate tests that trigger a precondition of an assertion. So at the top in this slide, in this picture, we see a road segment where dark gray or gray here, this is the pavement, and the yellow dots are our pedestrians, our agents. The red rectangle is the autonomous vehicle. And what we're interested in is whether the autonomous vehicle stops and prevents a collision when this is possible. Now, of course, depending on the speed of the vehicle, if you just jump in front of it at too close a distance, namely the stopping distance, then the vehicle has no chance and there's going to be a collision. So we're not really interested in any pedestrians that walk into that, because that's an unavoidable collision. Okay, so but we are interested in our test pedestrians walking into the precondition zone, because there is an assertion that says that when an agent is detected in this precondition zone, in this zone which is considered, in which it is considered possible for the autonomous vehicle to brake or maneuver to avoid a collision. So if the vehicle detects an entity in there, then it should brake. And so our assertion triggers exactly, that's just what I need. So our assertion triggers exactly at the point when a pedestrian, for instance, in this case, is detected in the zone. And so we wanted to find a good set of tests which trigger the precondition of this assertion. And our approach has been to program agents that respond to what they observe their environment to do. And what we have found is that the agent-based testing approach generates twice as many effective tests than can be done randomly or pseudo-randomly. This can be done efficiently, and the tests are robust as well as natural in terms of the behavior of the pedestrians. So what you can see at the in the middle here is a grid world type approach, and at the bottom we see the actual visualization in the Carla simulation. Okay. We also are developing a gym environment for this area. That's an adaptation of the OpenAI gym for the CAV community. It allows us to have multiple agents. So the red one is the vehicle that we're not controlling. Well, that's the autonomous vehicle. And what you can see is zones that allow us to see where braking zones are or assertion zones. We can also see or determine occlusion. So if you look in the middle, the pedestrian crossing, we can see when a pedestrian is occluded from the area that the red vehicle can perceive. And that allows us to explore a joint action space, gain theoretic focus, and also allows the generation of complex tests in terms of sequences of interactions between multiple agents that are involved in a test environment. So if you're interested in using this, contact us or just download it from GitHub and let us know how you're getting on. This is currently the focus of our work, especially as we are moving towards generation of far more complex sequences for assertions that go beyond the simple one with a pedestrian walking in front of a vehicle. Okay, and that gets me to challenges in the domain. I think the biggest challenge that we're facing is specification. It's essential to perform verification and validation, but I think as a community, we really need to step a step back and think about the specification for the systems we are looking at, the autonomous systems, and in particular machine learning based systems. I think specification is a particularly hard challenge, and as so many of you will know that Bristol has the TAS functionality node, and specification is one of the areas that we are tasked with. And so we are clearly looking at specification from different angles, and I think this will be a challenge for all the nodes for us to establish how to go forward with specification, which is the starting point for all the other activities, I think, and so therefore ought to be taken very seriously. The other important aspect is automation. We need to do far more automation, because the automation we had to put into place in order to get to the interesting parts of the research through coverage-driven verification allows us to do really interesting things, but unless you are prepared to put that extra work in up front, you don't get to the points that are interesting, especially when it comes to simulation-based verification. And so that is why we are providing the CAV-Gym for the community to use, so that not everyone has to go through the process of inventing environments that make it interesting for an academic to work in this area. And then I think we need far more innovation. We need creative combinations of techniques, and we need to become far more clever when it comes to verification and validation. And we need to exploit AI far more rigorously, especially also as we don't need to we don't have so stringent requirements as those who use the AI for the actual applications. We can cheat in verification and validation. If it gets me to the interesting case faster, then I'm allowed to do this for verification and validation, because I don't have to verify that part. So I'm interested in intelligent agency-directed test generation, online testing, verification environments that learn and get us to the data that we need in order to convince ourselves that the systems work as we want them to work much faster. Right, so I would like to thank you for listening and for bearing with me. These are all the people and researchers in particular that work in the Trustworthy Systems Lab, with various contributing to this particular area, and our funders. If you want to know more about our research, you can find our website up here, or you can contact me and I'll get you in touch with those who are working on the particular areas. Thank you very much.
Thank you very much, Kerstin, for this very interesting talk. We have already had a few questions posted in the chat box, but maybe we start with the live questions and then I will read up some of them as we go by. So Jan, please go ahead.
Thank you very much, Kerstin, for this very enlightening talk. I enjoyed that as usual, I would say. And I have one specific question. Getting to more interesting test cases is one thing. The other thing is that we will be overwhelmed with the large number of test cases to be performed for thorough testing to decide whether a system is trustworthy or not. Do you think it might be a good idea to re-evaluate the topic of equivalence classes? Because while you were presenting different traffic scenarios or robot scenarios, it came to my mind, in many situations, one could derive intelligent equivalence classes, and then one could argue that one representative test of such an equivalence class would be enough.
Yes, I think this is a really important thing to do. Going by my experience in hardware verification, that is already being done, right? So if you think about complex processor designs where they have, in the order of several hundreds, if not thousands of instructions to deal with, they just simply can't run every instruction after every other one, although this is often a coverage requirement for complex pipeline processors. So what they do is they find equivalence classes and say, okay, in some way, all additions and subtractions are the same with respect to what I'm interested in, so I only sample some of them. And so that is something that is being used actively in that domain. Of course, the domain we are looking at is much more complex.
Yes,
So,
wouldn't you agree that you need kind of a novel theory of equivalence classes, because we are now working in an n-dimensional space and not just with numbers that are considered equivalent?
yes, absolutely. This is really important. It's important for checking, and it's important for coverage as well. And in particular, it's important because these systems, although we may think the test is the same, these systems may not react the same. So identifying these equivalence classes is also important for trust, because as humans, it's important to understand what the system does. And so, not only should there be engineering solutions for this, and that's really important to manage complexity, it's also important for us to understand when what we consider the same in terms of the equivalence classes for the purpose of checking and coverage, do humans actually classify this as the same, or is it different? Which adds another dimension, because ultimately these systems need to be trusted. And that means we have to make them trustworthy. So it's also important to factor that in. But this is a really interesting area, and we're looking at Bristol at the moment at a proposal to address this, both from the human side as well as from the engineering side. And it's very, very challenging. This is not easy to do. This requires a completely different approach compared to the nice discrete or the multidimensional world that we've been living in before.
Okay, thanks very much.
Thank you, Jan. Thanks, Kerstin. So I will read up one of the questions from the chat box until someone else raises his or her hand. There was a question at the beginning of your talk about the picture you presented about those heat maps for various operations. And the question was, can this knowledge be incorporated in designing compilers that reduce energy consumption? And do such compilers already exist or not?
Interesting question. We are in the process of making one of those. So directly, this can't be done, unfortunately, because it's not, for this particular processor, it was possible to do because it was a very special processor. But in general, you will characterize based on combinations of instructions. And we have done this in a project which is called Team Play. So if you Google it, H2020 Team Play, you will find our current work in this area, where we've used models, regression-based models for the ARM M0, Cortex M0. And these models are sourced by an energy analysis tools, which does worst-case execution time analysis, but it uses energy values. That does not get you to worst-case energy consumption, I must say. So it gets you an energy consumption approximation, which doesn't have the properties of safety and tightness. But it gets you something that can be done at compile time. And we're now using this with a compiler that is being developed at the Technical University in Hamburg, WCC, which is exploring different options and optimizing with respect to time, energy, and also security levels. So you get a better understanding of these non-functional properties for your code, and you can pick the one that fits your requirements best. So yes, we are doing this, but this is leading edge research. But good spot. That's really what you want to do. You want to be able to give developers and the tool chain an insight into the energy consumed by their code. And at the moment, we're all trying to be more friendly to the planet, but the problem is we can't see the energy consumed by the code we write. Okay, and what you can't see, you can't optimize. Right? What we know is that this goes out of battery faster, right? We know that that's when we notice that something could be done better. But when we plug our machines into a socket, then we don't usually take energy consumption to be a first-class system design goal. And in the Team Play project, we do time, energy, and security for embedded and cyber physical systems. So have a look at that and some of the deliverables, and you'll see how far we've got so far. We'll finish in June, so if you're interested, we'll have a workshop then.
Okay, thank you very much. There are a couple of more questions again in the chat box. I will read one of them. I think given the time, we may have to end, and there could be an email discussion or a discussion later on. There is a question about your agency-based test generation. If I read the question well, and I'm not entirely sure if I'm reading it well, the question suggests that you are assuming a kind of a fixed behavior for your AB, for example, a fixed braking distance, and that might change depending on the situation. Does that influence your test case generation? Maybe I can read the question, but should the AB be expected to foresee the hazard situation and reduce the speed to reduce the stopping distance? That's the question.
So the whole point of using agents is to be able to react to how the system under test behaves. So this is a really interesting question because we're not controlling that system, and often we also don't have insight into how it's programmed, right? Because for us, it's a black box. We are almost like the third party that is being given the task to test the system under simulation, in a simulation environment. And because we don't know what the system does, we have to be flexible, because it can't be that in my test I'm assuming a certain behavior of the system and then my test hangs because the system doesn't do what I've hardwired into my test to expect. And that's exactly the challenge with the autonomous systems. It is not possible in a test to enumerate all the possible responses from the system. As such, the system under test is what is called a responder. It responds to its environment, and it is free to decide what to do in response. Now, some of these responses might be valid in terms of the traffic regulations, and some of these responses might be violating the traffic regulations. And we are there to spot the difference, right, and to identify violations. But the system is effectively free to do what it likes, and that shouldn't mean that my tests get stuck, which is why we're using agency in the test environment to at least get the test to a point where it completes. So effectively, our test agents are agile, if you see what I mean.
Yeah, I think that was a clear answer. Thank you very much. I think this is now time to conclude this very interesting lecture. Very interesting talk. Very interesting and thought-provoking points to follow up on. And there is email address of Kerstin. I see there are more questions, so perhaps you could follow up on those questions with Kerstin later through email. Kerstin, thank you very much once again for this very interesting talk. It was an honor, pleasure to have you. In 2 weeks' time, we will have Yanis Demiris from Imperial College, and he will talk about assistive robots. The exact title is on our website. I hope to see many of you in 2 weeks with Yanis's talk. Thank you very much all for being here, and see you in the next talk. Thanks.
Thank you very much.
Bye.
Thank you. Bye-bye.